All right. So, hello, grade 11 university and grade 12 college physics students. This is Mr. Musklow, and I've turned into a little bit of a YouTuber, I guess, because this is actually a YouTube video that's included with today's material. So, in normal circumstances, I wouldn't do this. I wouldn't include a video recording of me giving the day's lesson on a day that I'm away from school and a supply is in. But just with the circumstances this week, since I'm isolating, and I will be isolating for a few days, I thought that it would be helpful for me to just include some videos of me explaining the material that you're learning about. Okay, and basically, the idea is that this is the next best thing to me actually being in the class, explaining this to all of you in person. And so today I'm just going to explain section 13.1, which is on electromagnetic induction, and 13.2, which is Lenz's law. Now, section 13.1 on electromagnetic induction was a section that you actually had a chance to look at yesterday already. So students were to read that textbook section and complete some textbook questions. So hopefully the material in section 13.1 is going to look familiar. But I still thought that it would be helpful for me to explain it in this PowerPoint because I find, particularly with electromagnetic induction, it's just the sort of thing that you have to be shown in order for it to make sense. It's not really the most ideal topic to learn about by reading in a textbook. So I'll explain how electromagnetic induction works. We'll go over that. And then 13.2 is on Lenz's law, which is not something that you had an opportunity to read about yesterday. That's completely new. So I'll go through this PowerPoint like I usually do. And then, like usual, you'll have some time to work on the textbook questions after I'm finished the PowerPoint. Now, if you end up finishing the textbook questions, you also have a culminating assignment to work on. So yesterday I did post the culminating assignment. And the assignment, basically, for those of you that have read the instructions would know, it's basically to create your own physics problem. And so today, if you end up finishing the textbook questions, you can get started on that. Perhaps you can start brainstorming some ideas for what physics problem you want to create for your culminating assignment. Okay, so you definitely have lots to do today. Now, with regards to this PowerPoint, we'll start off by talking about electromagnetic induction, and that's what this opening slide is depicting. This is an image that's showing an illustration of what Michael Faraday used in order to understand how electromagnetic induction works. So hopefully by the end of this PowerPoint, you'll kind of have an idea of what's going on in this image, so that you can kind of understand the physics of what's happening. All right. So 13.1 is on electromagnetic induction. We know already that an electric current in a conductor can produce a magnetic field. When you have a current flowing through a conductor, we know already how to determine the direction that the magnetic field is pointing. We have our right-hand rule. We line up our thumb in the direction of the current, and then our fingers curl in the direction of the magnetic field. And so the magnetic field basically forms closed loops around the conductor, as we've learned. But in the early 1800s, physicists wondered if perhaps the opposite could be true. So they wondered if maybe a magnetic field could end up creating an electric current in a conductor, if you could do the reverse. And in 1831, an English scientist named Michael Faraday proved that you could do that. And this is a picture of Michael Faraday. This discovery that you can produce an electric current in a conductor with a magnetic field might not seem like a very important discovery, but we'll be learning later that it's actually an enormously important discovery. I want to say probably At least 90% of electricity that is generated today is generated by using this principle of electromagnetic induction. So it's an enormously important discovery, even though it might not seem to be super exciting at first. All right, so what is the law of electromagnetic induction exactly? Well, you had a chance to read about it yesterday. So I'm just going to say what the law says, and I'll then explain how it works. So the law of electromagnetic induction says that any change in the magnetic field near a conductor induces a voltage in the conductor, causing an induced electric current in the conductor. Okay, so what does that mean exactly? Well, this is the point where I say, it's helpful for you to actually see how it works and to be shown how the changing magnetic field produces a current. So that's why I have this link to a PhET simulation. You've probably noticed that I quite like PhET simulations. They're often helpful to show different physics concepts. So let's open this up. All right, so this is our PhET simulation. This is going to help us understand electromagnetic induction. So what do we have going on here? Well, we just basically have a wire attached to a light bulb. And you can see that the wire has been looped around in a coil. And you can see that the light bulb is not lit right now because it's not really hooked up to any voltage source. But we do have a magnet. Here's our magnet. And so I'm just going to take this magnet and watch what happens. I'm actually just going to turn off the sound here. So here's the magnet. You'll see that if I just plunge our magnet into the coils here, that our light bulb ends up lighting up. Now, the key here is to understand that the bulb is not lit when the magnet is just sitting here not doing anything. And to make clearer how this works, I'm just going to check off our field lines here so that we can actually see the magnetic field from our magnet. So clearly there is a magnetic field where our conductor is here, but you can see that having the presence of a magnetic field is not enough to actually induce a current in this wire. If you want to induce a current in the wire, the magnetic field needs to be changing. And this, in fact, is why, I go back to our PowerPoint, this is why I underline the word change. This is important, okay? It's a change in the magnetic field near a conductor that induces an electric current in the conductor. And that's important to understand. Okay, so again, how can I change this magnetic field? Well, one way to do it certainly would be to move the magnet. So you can see if I'm moving the magnet, that the magnetic field changes. And so as I move the magnet, our light bulb lights up. Another way that I could change the magnetic field would be by flipping the magnet around. That would also do it. I could also move this coil instead of moving the magnet. That could work as well. Okay, so there's a variety of ways that you can change the magnetic field here. But the important thing is that the magnetic field changes. Okay, we need to have a changing magnetic field to induce a current in the wire here. All right. So that's the law of electromagnetic induction, basically. Now, there are several factors that determine the amount of current that can be induced in this way. So one factor is simply whether the conductor is coiled or straight. So in this PhET simulation, we have coiled conductors. Even if the conductors were straight and you just kind of moved a magnet around near them, you would induce a current in the wire in that way. But it's not going to be as effective as when you coil them and plunge the magnet into the coil. So whether the conductor is coiled or straight, that's going to affect how much current is induced in the conductor. The number of loops in the coil also matters. So let me just go back to our simulation here. And what was shown on that slide was what you can do in the simulation. It's kind of cool. We can show the current that would be induced if you only have 2 loops, and then the current induced if you have more than 2. This one has 4. Okay, now things get kind of laggy here when I'm recording a video and also using this PhET simulation. I really need a new computer. So I don't know how well this is going to work, but we're just going to try it here. Okay, so if I move this magnet back and forth in the coil, it has a lot of loops in it. You can perhaps see that the light is getting bright. Whereas if I do the same thing in our coil that only has 2 loops, it's not getting quite as bright the way I'm seeing it. Okay, so the number of loops matter. If you have more loops in the coil, a greater current is going to be induced in the conductor. Okay, so the number of loops in the coil matters. The rate of change of the magnetic field also matters. So what does that mean exactly? Well, that's just basically how quickly the magnetic field is changing. And so let's see that in action. I'll just get rid of one of our coils here. All right, so the rate of change of the magnetic field is another factor. Here I'm going to move the magnet slowly. And you can see the light lighting up from moving the magnet slowly. And you can probably imagine that if I instead do this more quickly, that the light ends up lighting up even more. So here I'm moving the magnet more quickly than I did before, and you can see there's more light coming from our light bulb. And so this means basically that if the magnetic field is changing more quickly, there's going to be more of a current induced in the conductor. So how quickly the magnetic field is changing is what we refer to by the rate of change of the magnetic field. Okay, and then the strength of the inducing magnetic field matters as well. So if you have a really strong magnetic field that's changing quickly versus a weak magnetic field that's changing quickly, the stronger magnetic field is going to induce more of a current in the wire. Okay, so these are all different factors that affect electromagnetic induction. And of course, if you're in the business of generating electricity, this is important. So you're going to try and get as much of a current induced in the conductor as you possibly can. Okay, now before I continue, I'm just going to exit out of a little PhET simulation here so that it's not bogging my computer down. All right, now there's a couple of slides that explain some different applications of electromagnetic induction. And this is kind of interesting, I think. So one example of a device that uses this principle is induction cooking. So induction cooking is kind of cool. If you have an induction stove, basically materials will only get hot on the stove if they're made of metal. So we can see that taking place in this image. This pan is heating up on the stove, but the chocolate is not getting hot here because it's not on a metal pan. And so how does that work exactly? Well, it uses this principle of electromagnetic induction, as it turns out. Basically, in an induction cooker, you have a rapidly changing magnetic field. Okay, so underneath this pan, there's a magnetic field that's rapidly changing down here. And so if there's a rapidly changing magnetic field, there's going to be currents inducted in the pan. Okay, in the same way that with our PhET simulation, we changed the magnetic field by moving the magnet back and forth, and that caused a current in the wire. If we're changing the magnetic field beneath this pan, there's actually going to be a current induced in the actual pan itself. And so there's basically going to be electric currents like flowing around in circles in this pan, which is kind of, I know, strange idea. And so whenever you have this electric current moving around in the pan just ends up heating up naturally because of some resistance in the metal. And so that's actually what causes the pan to get warm whenever you place it on an induction cooker. This is why, if you have an induction cooker at home, you shouldn't wear a metal ring while cooking with it, because if you're wearing a metal ring, there's also going to be a current induced in that metal ring, and it could end up getting hot. So basically anything metal in the vicinity of this induction cooker is going to have currents induced in it, and that's going to cause it to just naturally get warm. So that's how an induction cooker works. Now, metal detectors, it turns out, also use this principle of electromagnetic induction. So here's how a metal detector works. There's a coil inside the metal detector that generates a rapidly changing magnetic field. And so that rapidly changing magnetic field is going to induce a current in any metal that's near it. So let's say that this individual has, I don't know, a metal watch or something in their pocket. If this metal detector is generating a rapidly changing magnetic field, then there's going to be a current induced in this person's watch if there's some metal in it. And now that induced current is going to generate its own magnetic field, as it turns out. We call this the induced field. And sensitive measurements can be made that actually pick up that induced magnetic field. So there's actually sensors inside this metal detector that are able to pick up the induced magnetic field that's created. So yeah, basically the metal detector has a rapidly changing magnetic field. It induces a current in a piece of metal, and then that metal generates its own magnetic field that the metal detector picks up. So that's how a metal detector works. It also uses this principle of electromagnetic induction, as it turns out. So that's kind of interesting, I think. All right, now section 13.2 is on Lenz's law. This is named after a Russian physicist who formulated a law in order to determine the direction that an induced current will flow. So let me just go back here. With our FET simulation earlier, whenever we plunged the magnet into our coil, we said that there's a current induced in the conductor, but we didn't really talk at all about what direction that current flows in. And using Lenz's law, you can determine what direction that current flows. And so we're going to learn about how that law works. And it's kind of an interesting argument that's used to figure out the law. All right. So, in order to understand Lenz's law, it's helpful for us to just return to our example of a magnet being plunged into a coil of wire. So whenever we, again, have a coil of wire and we plunge a magnet into it, that's going to cause a changing magnetic field around this conductor, and so there's going to be a current induced in this conductor. And the question we're trying to answer is, what direction does the induced current go in? Okay, and so here's the argument that Lenz used in order to determine the direction that this induced current must go. He actually determined the direction by using the law of conservation of energy. And here's how it worked. We know that plunging this magnet into the coil is going to induce a current in that coil. And now if there's a current flowing in that coil, that current is going to generate a magnetic field. And the name that we have for this field I mentioned earlier, it's called the induced field. Okay, so this is not the magnetic field of the magnet. It's the magnetic field that is induced from this current that's created. And so what direction is this current going to flow? Well, let's consider the two possible directions that current can flow through the coil. This slide shows one possible direction. So it's flowing in this direction upwards on this slide. And if that induced current is flowing in this direction, you can see perhaps that the solenoid is going to generate a magnetic field where this end is the north end of the magnetic field, and then this is the south end. Okay, we've talked before about how the magnetic field generated from a solenoid looks like a bar magnet. And so we're considering the case first where the induced current is creating a magnetic field that looks like a bar magnet with its south end here and its north end here. So this is one possibility. Now, in this hypothetical scenario, the induced magnetic field makes the right end of the coil a south pole. And that south pole is going to attract the magnet because we're plunging the north end of our magnet into the coil here. And so Lenz reasoned basically that this situation cannot happen. This is not possible. Doesn't make sense. Because if the induced field creates a south pole here, this magnet is going to be attracted to that south pole. And so if it's attracted to that south pole, the magnet's going to speed up. And then if the magnet speeds up, it's then going to induce a larger current, which would speed up the magnet further, which would induce a greater current, speeding up the magnet further. And you kind of have this situation where you're basically creating energy out of nowhere. If this becomes the south pole of a magnetic field, the magnet's just going to keep speeding up as it goes through the coil on its own. And so this doesn't really make sense. This violates the law of conservation of energy, which says that you can't just create energy out of nowhere. And so Lenz reasoned that this situation does not actually make sense. It cannot be the case that the right end of our solenoid here is a south pole. And so he said instead that it must be the north pole on the right end. And so this moving bar magnet then is going to induce a current in the coil. And that current is going to generate a magnetic field that opposes the motion of this bar magnet. So in other words, this bar magnet is getting plunged into our coil, and the reason why a north pole is created here is basically to oppose the motion of this magnet as it's getting plunged in, so that this plunging magnet is repelled from the magnetic field that's being created. Okay, so I think this is the last slide. Yeah. So this is what Lenz's law says in words. It says that if a changing magnetic field induces a current in a coil, then the electric current is in such a direction that its own magnetic field opposes the change that produced it. So that's like a lot of words. You know, what does that mean exactly? Well, just basically look at it like this. The coil is going to oppose whatever the magnet is trying to do. So we have in this image the north end of our bar magnet being plunged into the coil. And so how is the coil going to respond to that? Well, it's going to generate a magnetic field that opposes what the magnet's trying to do. So it's going to create a magnetic field with its north end here, and that north end will oppose the magnet. Okay, and so that's basically what Lenz's law says. That's how it works. And that gives us a way of determining what direction the induced current flows. Okay? And that's that. So it would be at this point in the lesson that I would ask if anyone has any questions. But I can't really do that because I'm just explaining this in a video. So certainly if anyone has any questions, you're welcome to just send me any questions and I'll be happy to answer them. But yeah, we'll just leave it there. Now, as I said earlier, you do have some textbook questions to work on now. So those textbook questions are posted in Google Classroom. I didn't include them in the handout because I didn't want to waste paper. I just basically wanted the 12 slides on the one sheet of paper without having to attach another piece of paper. So yeah, the textbook questions are in Google Classroom. So you can spend some time working on those textbook questions. And as I said earlier, if you finish those textbook questions, then you can just work on the culminating assignment that I posted yesterday. Okay, so that's all from me. Good luck. And yeah, have fun.